Hello everyone. In today's recording, I would like to show how to perform full acoustic calculations in the iXCharm program. And until now, it was possible to perform acoustic calculations using the acoustic calculation calculator. However, there was no possibility to calculate the attenuation of ventilation ducts, which, despite its high utility, somewhat limited the capabilities of this module. However, now with the latest update, we have released the ability to calculate the attenuation of channels, which is additionally implemented through the pressure loss calculator. And therefore, moving to the main point, this is how the main window of the pressure loss calculator currently presents itself. As you can see, a whole window with noise in individual octaves has been added, and the fittings, including the fan, silencer, and so on, have been slightly expanded. For the purpose of this presentation, I prepared a small ventilation system diagram which shows a noise source in the form of a fan, the noise suppressor as a damping element, and the duct system delivering air to individual rooms. This system is essentially built from fittings with a diameter of 200 and 125 millimeters when supplying air to the diffusers into the rooms themselves, which I will soon show how to carry out. This entire module is based on calculations on the research of a certain Mr. Reynolds, and who developed certain methods for calculating noise quite some time ago, back in 1989. The suppression of noise inside ventilation ducts. And based on this knowledge, algorithms have been prepared that calculate the attenuation of the fittings and ventilation ducts. Alright, so let's perhaps start with beginning the calculations. I'll take another look at the drawing. So we start from our source, which is the fan. Then there will be the silencer, followed by a section of the straight duct with a length of 1 meter. Then we will have an equal diameter T. We will have here a section of duct with a length of 4 meters, 1 meter section, reduction, flexible transition, and the air vent blowing into the room. We will calculate the noise level generally in this room at a distance of 1 meter from the air vent, and it will be the sound pressure level, which is worth noting, not the sound power level, because our ear perceives sound sensations through just acoustic pressure. However, we define all these elements by providing acoustic power. Alright, let's move on to the program. First, we select our source in the form of a fan. Here we select a diameter of 200. Flow, we choose 300 cubic meters per hour, because that is the total airflow. And we define the sound power level either in decibels or in decibels corrected with a weighting. Typically, it's the aweighting provided by manufacturers, but there are cases when it's just regular decibels, which the program will have to correct with a weighting, which is most appropriate. Regarding how our ears perceive auditory sensations, now we need to define these levels of acoustic power and preferably take them simply from the selection of a specific device. And here, for the sake of this presentation, I selected this type of Haman ARRI 2090-50 EC fan, which is characterized by such acoustic parameters. Here I suggest never looking at the sound pressure level, because these are always tainted data, as the manufacturer has to assume many other parameters in some way. Regarding either the room, the sound absorption, the volume, etc., I would approach such data with a great deal of caution. The most important is the sound power level. I will now transfer this window to the second monitor so I can transcribe these values effectively. And here we have the outlet sound power levels from the fan with the following levels. That is for the installation 36, 48. Next we have 54,
49, 53. 53 or 40. 45 and 37.
37 here. Background noise is in a sense 0. Okay. All right. We had the fitting. Next we had a noise damper, and here again we need to define the parameters concerning the attenuation of the damper as well as its noise, because this is also an important parameter describing the silencer. Very often we may find ourselves choosing a silencer and it has very good attenuation parameters. The only thing is that it may not be here problematic in terms of the fact that the higher the attenuation of a given silencer, it can generate higher noise. Because if the manufacturer assumes that this attenuation is achieved by increasing the number of baffles, then within the silencer the head-on airflow speed increases, and this speed causes self-noise to occur, and therefore a good silencer manufacturer should always provide these two values simultaneously, so that it does not happen that we choose a silencer with very good soundproofing, but it ultimately has enormous self-noise and can sometimes generate more noise than its soundproofing level, which is why this should also be taken into consideration. Here I used the Trox company's Easy Product Finder program for this presentation, and we can choose some silencer from here that will best suit our installation. For example, we can initially install this type of silencer here. Which is characterized also by such self-noise at a level that is very low, practically inaudible. I am also switching to another window to better rewrite it. So I am rewriting the attenuation regarding each octave.
13, 23, 37, 37, 33, 23.
15. The self-noise is basically everywhere here at the level of 15 or below 15. So I then enter under 15 in brackets. These noises will essentially be inaudible. So it is, you could say, entered pro forma. With such values, we won't generate any noise audible to the human ears. All right, we are adding the fittings. Next, we had a piece of straight duct with a length of 1000 millimeters. Here, the attenuation of this fitting is automatically calculated based on Reynolds testing, and the intrinsic noise based on velocity. Here we basically have these parameters. Without changes, we add the fitting. Next, we had a straight through T.
Enumerated skills.
Since we are currently calculating the noise in this room, we need to select in the calculator that it is a branch, not a through flow. It is a distribution, that's correct. And we indicate that it goes here to the second branch. And the branch channel, cubic meters per hour. Okay, we add it. Now we had a section of a straight channel with a length of 4 meters. So we choose the straight piece again. 4000, here the skills are calculated.
We look. Elbow 90 degrees.
It could be flex or a 5-second log, although from the perspective of acoustic calculations, it does not matter at all. Okay, we're adding a piece. Oh, sorry, because we're constantly filling in the usable value for the air storage provided. Here, for this simple task, probably also
I hasten naked.
Now we're adding a strict piece again. We had a 2 meter one here. 150 is already correct. We're adding a reduction to 125, so from 200 to 125. 150, everything matches here. The attenuation for this fitting is practically zero. The self noise, as you can see, practically doesn't exist due to the low flow speed, which here is only 1.3. Later we had flex, a flex section. We can also set the length. We select 120 diameter.
90. Let's look around.
Here, the flexes are characterized by quite high damping, it must be admitted. However, it was shown in studies and calculations, so I'm not arguing with that. Personally, it seems a bit much to me, but okay. And the last element was the diffuser.
I can't see.
In our calculations, we don't define whether it is a diffuser with or without a plenum box. Here, its acoustic parameters. We'll generally define it. So it is essentially the symbol of the terminal element in the form of a supply vent or an exhaust vent. Whether it is an element with a plenum box or not is simply defined by acoustic parameters. And here again, the program calculates the noise of such an event. Nevertheless, if we have some very good technical parameters, we can read them from the manufacturer's data. If not, we either set them to 0 or leave them according to the calculations that are here. And now self-noise is also automatically calculated based on the airflow velocity. And we need to define the sound power level based on the selection card of the diffuser. I have again, for the purpose of this presentation, selected a diffuser. Using the Trox Easy Product Finder program again, I selected a VDW diffuser, Arza HML 300 by 8. Which is characterized by such acoustic parameters at this efficiency when placed centrally in the room. And I move it again to the second monitor to write down these values.
And here we have, for the octave, 63 Hertz, 36, 36, then we have 29, 34. It will latch on 25, 23. And then we have just the values, very low, 15 decibels. Okay, we add the fitting.
And basically this way we have created here from the source through the muffler to this diffuser. And now we want to know what the sound pressure level is 1 meter from this diffuser, and that's why it's called a full calculation, because we can do it in other software. I haven't found a way to automatically simulate these values here. When we look at the attenuation results, they basically can't tell us much about what the sound pressure level will be. In the room itself, we basically have to simulate it elsewhere. And for this purpose, we have an acoustic calculation calculator, which has also been modified for this here. For conducting full acoustic calculations, meaning we copy to the acoustic calculation calculator and computer the level of acoustic pressure 1 meter from this diffuser. Here we provide the parameters of this room. Meaning we have a room 3 by 3 by 3 meters at a distance of 1 meter from the sound source, which is our diffuser. Here we choose the sound absorption coefficient depending on the finishing of this room. I assume that this is a room that is acoustically dampened in a standard way, so a typical office room that is furnished with carpets, etc. So we indeed select over 0.15 here. And the directivity factor depends on the location of such a diffuser in the room. Here we have situation A, meaning the diffuser is centrally placed on the ceiling, and it is 1 here. So we select it here as well. The heat the sound power was defined as a level corrected by the awaiting characteristic, and here we have it. All these values are transferred here and calculated from our previous tool. And now we can simply click calculate and check what sound pressure level has been set in this room. And it is 36.4, so quite a decent value. Whether this is a lot or a little depends on the type of room and what we want to achieve. However, of course, we can aim to reduce this noise by, for example, using a different silencer. And for example, we can go back here to our tool, enter the silencer edit mode, either by right-clicking and editing the fitting or by double-clicking. And let's return to our silencer selection program. Let's pick a slightly better one here. I see, oh, this one is very good, although it will have higher self-noise. Because here the front flow speed through it is 7 meters per second. But for the sake of our example, we can check how it will affect the sound pressure level in the room. Here we have the noise levels and attenuation. I transferred this to the second window. Let's see what comes out of this. Okay, so we have here attenuation.
2, 10, 17, 29, 39, 41, 41, 40, 32, all the best.
The inherent noise, well, here I already have a fairly significant increase, 34.29.
24.
Further, very low, below 1 centimeter, we accept, we copy. For our logistical calculation calculator, we calculate.
Oh, not much has changed.
You could say that nothing, and it's probably due to the fact that the diffuser itself can have quite high acoustic parameters and should also be adjusted. The silencer itself was not able to significantly improve our acoustic parameters. After performing such calculations, we can export them to Excel as a report. Here we enter the name of the project, the investor, and the designer who performed these calculations. We click OK to confirm. They support our calculations in the form of such a report table. We can do the same with pressure loss calculations by clicking for export in the same way. And that's basically it. Of course, we can keep experimenting here later, see what would happen if we had a better soundproofed room. You can already see if we had a room slightly acoustically dampened, curtains, windows, carpets, and so on, then for those parameters the sound pressure level would be 34.1. And if it were a very, very well dampened room, well, we would have 32 decibels for such an arrangement of fittings and an air vent. What is nice about this module is that we can actually carry out these calculations from the beginning, from the very source, up to the user's ear. However, as you can see, it is quite time consuming, labor intensive, and performing these full calculations is not always justified. Nevertheless, there are many situations that can somewhat save our skin, because unfortunately acoustics is quite a sensitive subject, where due to the multitude of all these parameters, decibels adjusted by the A-weighting, sound pressure, the acoustic absorption of the room, the volume of this room, it is also a very difficult issue. Thank you for your attention. I hope this tool will be useful to you. You will use it. Thank you and goodbye. Bye.